No, but it just picked up what you said there. All right, so we are talking about problems 5 and 6 in Force 1 right now. All right, now I showed you a kilogram in class. It was that brass piece. You guys rolled it around with your fingernail, right? Now, what is it that makes this thing have mass? It's got stuff in it, right? It says a certain amount of protons, neutrons, and electrons. Now, the concept of number 5 was that first off, A through D, you should have 1.0000 kilograms for all of those. What does 1A, B, C, and D ask you about? It's as if you take this thing to somewhere else. If you take an object and you know its mass to some other place, unless you chop some of it off, or if it's a person and it adds some Twinkies or something like that, then it still has the same amount of stuff inside it, so its mass has unchanged. If you calculated anything for A, B, C, and D, it actually shows a really serious conceptual lack of knowledge. You should have calculated nothing for those. There's nothing to show. If you calculated something, it shows me that you don't understand what you're doing. You should have calculated nothing. Matt, you with us? Good. Now, I gave you in the problem all of these values. That acceleration due to gravity on the moon was 1.62 meters per second per second. In DC, it was 9.80. In Denver, we have a slightly different AG. But I wanted to talk to you about why, because the problem doesn't really talk to you about that. So I'm adding to your knowledge right now. Whenever I review a problem with you, I'm always trying to give you more knowledge than just simply what mathematically did you have to do to solve the problem. So here's that more knowledge. Why are these different? The reason they're different is because gravity is dependent on the things that are in this equation. This is Fg right here. I can't draw on it while it's gone. This is gravity right there. That's the weight of the object. And everything that weight is dependent on is on the right side of the equation. G is a constant, kind of like the number half in half AT squared. AT squared isn't equal to distance, but half AT squared is. So that number's just always there. And you don't need to concern yourself right now with what number G actually is. What I really want you to understand is all the measurements that go into calculating the weight of an object. The two masses, M1 and M2. M1 would be like the object you're standing on. In most cases for us, it's Earth. But if you took an object to the moon, M1 would be the mass of the moon. M2 is, what is that object? If it's your pen, you're calculating the weight of your pen if you put the mass of the pen in as M2. If it's you and you put the M2 in as your mass, you're calculating your weight if you use this equation. Now R is the distance between them. You see that R is squared, so a slight difference in distance will get amplified in the equation. Now the reason R is squared in the equation is that the reality of gravity is the further you are from something, it makes a dramatic difference in the weight of the object. This is essentially why you don't fall off Earth and fall towards the sun. Because you're so much closer to Earth that the force of gravity between you and Earth is way more. So let's look at these three AGs. They're different. They're all on Earth. So what part of this equation is different in those three different places? It's R. In Denver, aren't you, it's the mile-high city. We're a little further from the center of Earth. So you actually weigh a little less in Denver than you would anywhere else because you are just a little bit further from most of the mass of Earth. Now clearly you're still 0 feet from the ground just like everybody else, but you're on ground that is higher, so that means the rest of Earth is a little bit further away. So Earth doesn't pull on you as hard in Denver. If you want to gain some weight, you can just go to sea level and you will weigh slightly more. Will your mass be any different if you go to sea level? Not as long as you don't intake or put out any stuff, right? We don't want to talk about that. That's all gross. So then when you went to go calculate E, F, G, and H, like what do these things weigh in different places, what you should have done to be able to do that is recognizing that the mass is the same in all the different places. So you take that mass and you multiply by the local AG. So E is the weight in Paris, so you use 9.81 meters per second. F is the weight in Washington, D.C., so notice I use the AG that's local to Washington, D.C. So, in summary, you take an object from one place to another. What about it is going to change? Its weight. And AG is different, so if you drop it, how quickly it will gain speed will be different. Now, the last one was the moon. What about this equation would be different if you're on the moon? M1's different. The mass of the moon is way different from Earth. Now, radius is also different. The moon's a lot smaller. You're closer to the center of mass of the moon. But the mass of the moon is so much smaller that that's why things weigh less on the moon. Now, I don't have you use this equation until later in circular motion, but I wanted you to see it right now so that you understood that if objects have more mass, they will end up weighing more. So if you go on a diet, what is it that you're really trying to lose? You're trying to lose mass. You want to get rid of some of the stuff that you carry around with you. Now, if you get rid of mass, you will also then weigh less. You don't really just want to weigh less without losing mass. To do that, you'd have to go to a different place where there's a different AG. You actually want to get rid of stuff. It shouldn't be called Weight Watchers. It should be called Mass Watchers. So that's 5. Let's take a look at 6. Questions? Say that one more time. All right, so we're moving forward to number 6. Now, the premise of number 6 is you're at McDonald's, and you got a quarter pounder. Now, as soon as you recognize you got a quarter pounder, you got to say, what is that? What does that mean? The quarter pound is its weight. So that's the pull of gravity on it. Now, question A asks you, what does that weigh in newtons? Well, you've got a weight, and what you want is a weight. How do you get from a weight to a weight? Unit conversions. So no equations necessary to do part A. You should have done a unit conversion like that. Does anybody have anything different right there? What do you have, Chris?
One on top and then 0.2248.
All right, so what you have there is 1 pound over, excuse me, you have 1 Newton over 0.224, and there's more to it, pounds. All right, do you see that 4.44 divided by 1 would be the same amount as 1 divided by 0.224? It doesn't matter which version of this conversion factor you use. You came up with the same correct answer, didn't you, Chris? Okay. But you can't mix and match these. It's one version of this conversion factor or the other. So you can see why I call quarter pounders Newtoners, because it's just about 1 Newton. Now in question B we ask, what's the mass of a quarter pounder? Now what we have right here is the weight of the quarter pounder in the metric system. If we want the mass, now we need an equation because weight and mass aren't the same thing. We cannot do a unit conversion. So the equation that gets us from weight to mass is Fg over Ag. Now, how do you know which Ag to use? Because in number 5, didn't we just give you a bunch of Ags? Well, how did you choose? Did you just use 9.81? That was right, because the question you should ask yourself when you're plugging in a value for Ag is, where was this thing weighed? And since we don't know where it was weighed, what we have to do is approximate. And if we're going to use an approximate value for Ag, we're going to use the average value, negative 9.81 meters per second per second. Now, if it were weighed in Denver, what would we put here? Yeah, we put negative 9.796 meters per second per second. And if it were weighed on the moon, we'd use the weight on the moon and 1.62 meters per second per second. What am I doing here? Yeah, but why are either of them negative? Yeah, because gravity pulls down. All weights are negative. So the quarter pound originally should have been negative the 1.1 newtons is negative. And so the two negatives cancel out, and you get a positive mass. What'd you get? 0.1 something? 0.113, so 0.11 kilograms. Notice that the mass comes out positive. It has to. Mass can't be negative because there's either protons and neutrons and electrons there or there's not. You can't have a negative amount of stuff. Just like you can't have a negative shoe size or a negative amount of time. So, is mass a vector? No, mass is not a vector. Is force a vector? Yes, it has a direction. Is acceleration a vector? Yes, it has a direction. But mass is not a vector.